Look at this web of dependencies. This is what building AI agents feels like right now. You are constantly wiring together disparate libraries and wrestling with fragmented tools instead of writing core agent logic. This infrastructure fatigue drains developer hours. Teams spend weeks trying to force the routing layer to talk to the terminal interface, often delaying new feature deployments by several months. PiMono is an all-in-one TypeScript monorepo built to eliminate that integration phase. It provides a unified stack for everything from LLM API calls to the user interface. The repository has secured significant traction, with 43,000 stars and 5,000 forks. It also maintains an active commit history, pushing nearly 4,000 individual updates. It operates under the premium pi.dev domain, which was donated by the community as a marker of the project's authority in the open source space. But there is a paradox in these numbers. This comprehensive ecosystem is maintained almost entirely by a single developer, Mario Zechner, known as Bad Logic. PiMono serves as an architectural blueprint for how a solo developer can manage and scale a software ecosystem of this size. This diagram illustrates the internal directory layout. By expanding into the 5 core packages, we see the advantage of a monorepo pattern. The modules lock into a vertical stack, preventing versioning mismatches. At the base is PiAI, the foundational data routing layer. This package abstracts the differences between OpenAI, Anthropic, and Google into a single API surface. You write the call once, and the package handles the specific provider formatting. Moving one layer up, we find the PiAgent core package. This logic center manages native state and executes tool calls internally. It eliminates the need for external dependencies to handle the agent's memory or action execution. To visualize the agent's output, the project includes dedicated user interface packages. For terminal-based interactions, TUI acts as the rendering engine. This split screen shows how the engine uses differential rendering. Instead of re-rendering the entire screen, which causes the flickering seen on the left, it targets and updates only the specific data blocks that have changed. Additionally, PiWebUI provides drop-in web components for migrating the agent interface to a browser without altering the back-end logic. This tightly coupled architecture is what allows a single developer to ship full-stack features without breaking the underlying integrations. The project is built on the ideology that artificial coding benchmarks are no longer valid measures of AI capability. Sanitized test suites are too clean. They fail to capture the friction of real-world engineering, where environments break and instructions are often ambiguous. PiMono offers an alternative, capturing messy, live session data directly from users as they work. To extract this data, the project uses a dedicated tool called PiShareHF. This schematic shows the process. PiShareHF pipes the context windows and prompt parameters from your local terminal directly into a remote database bucket. Crucially, it captures failed tool calls and the AI's corrective loops. That data is then routed into public Hugging Face datasets. Failure data is often more valuable for model training than successful path data. A model learns more by seeing how an agent corrects a broken script than it does from a perfect execution. Making this tool public creates a decentralized training pipeline that generates high-signal data from real-world tasks. In this way, PiMono acts as a distributed data harvesting engine, masked as a local developer tool. We have to look at the logistics of how one person manages 4,000 commits and thousands of users simultaneously. Repositories of this size attract a constant barrage of low-effort pull requests and redundant issue tickets. To manage this, the project uses an automated filter. By default, every new issue and pull request from a new contributor is automatically closed the moment it is submitted. This is handled via GitHub Actions, which instantly blocks contributions before they can reach the maintainer's inbox. This friction forces contributors to read the strict rules in the contributing.md file if they want their work to be considered. The maintainer then reviews the auto-closed queue on their own terms, manually reopening the ones that meet the project's standards. This boundary prevents maintainer burnout and ensures that the project's velocity isn't derailed by the administrative overhead of open-source noise. Automated boundaries are a logistical requirement for a developer managing this volume of input while maintaining high engineering throughput. The project consolidates the entire AI stack, from routing and state management to final terminal rendering. It couples this stack with a telemetry pipeline that feeds real-world failure data directly into public research datasets. But analyzing this architecture requires looking at its bus factor, the number of key developers who would need to disappear for the project to stall. For PiMono, the bus factor is precisely 1. This represents a risk for enterprise teams. Adopting an ecosystem entirely reliant on one individual means that if the maintainer stops, the entire stack effectively freezes. However, this risk is the exact trade-off that allows for the development speed seen in the solo maintainer model. If this breakdown saved you time, hit subscribe. We review the most interesting open-source AI tools every week, so you are always ahead. Now, if you liked this technical breakdown into AI agent toolkits, you are going to love our breakdown of the open-source memory layer that gives Claude persistent context across sessions. Ultimately, PiMono demonstrates how architectural control and rigorous data collection can bypass the friction found in fragmented ecosystems. Whether the solo maintainer model scales long-term remains to be seen, but the baseline it sets for agent tooling is undeniable. See you in the next deep dive.